Okay, Year 12, welcome to your video tutorial on decimal point to floating point conversion. Today we are going to have a look at IEEE754 and the representation of decimal numbers or floating point numbers in 32 bits with IEEE754. We're going to take a decimal number and convert it, and then take a converted number and show you how to get back to the original decimal. Okay, so the first thing that you have to do, the number we're going to use today, sorry, I'll throw it up the top here. The number in this example is going to be 22.625. It's a pretty steady example. It's pretty nice. It's all okay. So the first thing that you have to do in the very first step, step number 1, okay, is take this number here and convert it to binary. Okay, so it's going to be interesting because we're remembering we've got a decimal point in here. So I'm just going to lay out the underlying binary value, so when I do my conversion it's going to be really easy. Now, I know it's 22, so if I'm looking at binary, if it's 8-bit, it's going to go 1, 2, 4, 8, 16, 32. Okay, so 32 is bigger than 22, so I know I'm going to be starting at 16, 8, 4, 2, 1. I know my decimal point's here. I also know if I'm looking at binary, the first decimal place after that is going to be 0.5, 0.25, and 0.125. Okay, so that's binary. I know that from previous lessons. Okay, then if I'm converting this number, to binary, and I'm looking at 22, say, to start with. Okay, so 22 goes into 16 once. Okay, oops, I'm just going to change the thickness of that pen so we can see the difference. Goes into it once. That leaves me with 4, 5, 6 left over. So none there, 1 there, 1 there, 0 there. Okay, then my decimal point. Now, at this point, I now have to represent 0.625. I know that's the first thing I can go is in 0.5, which leaves me 0.125. So I'm going to go 0, and then I'm going to go 1. Okay. So this is the number that I'm left with, 10110.101. Okay, the second step that we need to do is to normalize the number. Okay, so we are going to move the decimal point to the first available 0. Okay, so if I'm moving this, I'm going to move it 1, 2, 3, 4 times. 1, 0, 1, 1, 0, 1, 0, 1. I've moved that 4 times, okay? So I also need to jot down and make note of that 4. Okay, this number here is my mantissa. So the mantissa for this is 0.110.101. Okay, the reason why I jotted down the 4 before is because that is my exponent. Okay, before I can write down, so I've got parts of the number. I know it's a positive, so I know what my sign bit's going to be. I also know that I've got my mantissa. I also know that the third part of IEEE754 that I need to represent is the exponent. The other really big fun fact I remember about an exponent is that exponents are stored in excess of 127. Okay, so the exponent is stored in excess of 127. So step 3, I just need to make sure that I add 4 to 127. So if I do my calculations here, 127, plus 4 is going to equal 131. So I need to make sure I represent the exponent in excess of 127. So I need to actually represent it as 131. So I'm just going to quickly jot down a binary, 8-bit binary down here, and I'm going to write it in, and I know it's going to be 131, so 128, that leaves me with 3. Cool. So I know 131 is going to be represented by 10000011. Okay, beautiful. Step 4, finally put it all together. Okay. So there's a lot of really important things here. I know that the sign bit is 0 for a positive number, 1 for a negative number. I also know in IEEE754 that is how the sign bit comes first. So 22.625 is a positive number, so there's a 0. I know the next thing that gets represented is my exponent. So 1, 1, 2, 3, 4, 5, 1, 1, and I got that guy from over here. Okay, and now it's my mantissa. I know my mantissa is this guy up here, so I'm going to throw him down, and he becomes 0, 1, 1, 0, 1, 0, 1. So those steps again, convert to an absolute value. Yep. normalize the number so you only have a 1 at the front. The excess to the right of that 1 becomes the mantissa. The number of decimal spots that you have to move becomes the exponent. Take that number of the number of decimal spots you used, use it in step 3 to work out the exponent. The exponent is stored in excess of 127, so make sure you add 127 to that number to get 131. Final step, put it all together. Sign bit, exponent, mantissa. And that's it, guys. That's taking decimal to floating point. We're about to go the reverse way. Okay, guys, let's work from the reverse way. So here I have a IEEE754 floating point number. Now, I have used the same number as the previous example, so you can see, you can make a correlation between the different steps, and if we use a consistent number, that's going to hopefully make it clear. Okay, so step 1. Okay, the first thing that you deal with if you have an IEEE754 number is you work out what the exponent was. So I know the exponent is stored in excess of 127. I am deeply aware of that. I'm over this and I know it off by heart now. So I go 128, 64, 32, 16, 8, 4, 2, 1. I know that the exponent is represented with the second section. If it's not split up into sections, I know the first bit is the sign bit and the 8 bits following is the exponent. So I'm aware it's stored in excess of 127, so I need to work out what it is stored as and then minus 127 in order to work out the exponent. Okay, so let's roll. Let's throw this down in here. We go 1, 0, whoopsie daisies. I'm going to undo that for a second. I'm just going to change my pen size. Thank you. 1, 0, 0, 0, 0, 0, 1, 1. Cool, and if I do that calc over the side here, that's 128 plus 2 plus 1. 128 plus 2 is 130, so I know it's stored as 131. Okay, like I've said 1,000 times, exponents are stored in excess of 127. So I minus 127 from that number. 11, 4, 2, 0, 0. I know my exponent is 4. That means in my second step, what I need to do is I need to take my mantissa. Okay, I need to start with a 1. I then need to throw in a decimal point, and I need to throw in my 0, 1, 1, 0, 1, 0, 1. Cool. I know my exponent is 4, so I then take this decimal spot and move it 1, 2, 3, 4. So I'm going the reverse way here. I then end up with 1, 0, 1, 1, 0, dot 1, 0, 1. This is now my number. Cool. This is excellent. 3, I then need to reverse, and this is my decimal value. That is the fractional part of my decimal value. So I need to take in step 3, 1, 0, 1, 1, and convert that from binary to decimal. So 1, 0, 1, 1, 0. I'm going to jot underneath this so I don't screw it up. 1, 2, 4, 8, 16. So this is going to be 16 plus 4 plus 2. So that's going to be 22. Whoopsie daisies, undo. That's going to be 22, and let's just for the colour sake work it out. Point. And I've got 1, 0, 1, so I'm again going to jot down my binary here. I'm going to go dot 0, 5, 0, 0.25, 0, 0.125. Beautiful. Cool. And I've got 1, 0, 1. Okay, so when I do this fabulous addition down the bottom, I'm now going to have 0.5 plus 0.125, 0.5, 6, 625, 625. The last thing that I'm going to look at is I know from here that the 0, the sign bit is a 0, so it's going to be positive 22.625. Ladies and gentlemen, that is how you convert a IEEE 754 number to decimal. First step, work out the exponent. Second step, use that number, use that exponent to manipulate the mantissa and do the reverse of what we did before. Cool. Then take the outcome of that particular calculation, convert the first part to the decimal number, convert the second part to the fractional number. Last but not least, check the sign bit, see if it's positive or negative, apply that sign to the number. Bob's your uncle, done and dusted.